Okay, this week we will discuss on the AC analysis of a BJT amplifier circuit. So this slide show the amplifier circuit. Okay, amplifier circuit consists of BJT, and then at the input we have the signal source, the input source, and then we have the output here. Okay, so the amplifier circuit. The actual amplifier circuit is the one in the big box here. So this is the amplifier circuit. So the amplifier circuit actually is the BJT connected in a bias circuit. So the bias circuit is used in order to enable the BJT to be in active operating region so that the BJT can amplify the signal properly. Okay, so and in the last week we have discussed on how we can determine or how we can calculate the operating point or the Q point of the BJT, which is the collector current, the value of collector current, and the value of collector emitter voltage VCE. Okay. In this week, so we will examine or we will analyze the performance of the amplifier circuit. To be specified, we will analyze on how good the amplifier circuit as the amplifier to amplify the circuit, to amplify the signal. So in terms of the amplification process, so ideally we want to have a very big the gain. So means that the resulted in voltage signal, output voltage signal must be much higher than the input signal. So we expect the amplifier to have a satisfactory value of gain. Okay, so actually the AC analysis of the amplifier circuit is related to what we have discussed in general model of amplifier. So in general model amplifier, so we have many parameters that we considered. One of them is input impedance, and then we have the output impedance, and then we also have the open circuit gain. So the open circuit gain of the amplifier circuit will determine how much the output with respect to the input signal. Okay, so in order for us to analyze the BJT amplifier circuit, we need to replace the BJT with appropriate device model. Okay, so actually the device model in general is a circuit element that approximate the behavior of a certain device, or the circuit element or the device that can imitate the operation of the certain device. So here we use the device model of the BJT specifically in the operation of AC signal. Okay. In general, there are two models commonly used in small signal AC analysis of the transistor. So one is RE model and the second one is hybrid pi equivalent model. So in this class, we will exclusively use hybrid pi equivalent model for our analysis. So the hybrid pi model is quite useful for analysis of high frequency transistor, and then at lower frequency the hybrid pi model can closely approximated to the RE model. Okay, what is hybrid pi model? So the left hand side diagram or figures is the symbol of BJT. So BJT has three terminal. We have base, collector, and emitter. So in general, we consider the base terminal as the input terminal and the collector terminal as the output terminal. So, and the collector current will be the output, and then the base current will be the input. But for the hybrid pi model, instead of considering the base current, so we're not considering the base current, so we will use the term voltage between base and emitter. So V pi is the voltage at base emitter terminals. So this you need to take note that this V pi, the V pi is not the same as what we have used as a VBE in the DC analysis. In the DC analysis, the value of VBE is a fixed voltage, but here in AC analysis, we consider the V pi as a voltage that fluctuates or keep changing according to the input signal. So according to the input signal. So V pi will be a variable rather than a fixed value such as VBE. So take note that V pi is not equal to 0.7. Okay, so this is the hybrid pi model. So between base and emitter junction, so in active operating region, the base emitter junction is in forward bias, and then at forward bias there will be what we call it internal resistance. Although it is in ideal model of the diode or PN junction, the forward bias PN junction can be modeled as a short circuit, but actually we need to consider the internal resistance. So internal resistance between base and emitter is represented by the R pi. Okay, R pi between the R pi. And then the base current, so we have it here, the base current. So we consider a voltage across R pi as a V pi. So the V pi is actually equal to the IB R pi. Okay, this is between base and emitter. Okay, between emitter and the collector, so we will have a dependent current source. We have this dependent current source to represent the relationship between IC here. This is IC and IB. Okay, so so in this model, you can see the collector current is depend on the value of V pi. So this is where you can see that the collector current is controlled by the base emitter voltage. Okay. So since this is if you see this model, this is the amplifier model here, is called a transconductance model because the output is current, and then the input is voltage. So this is can be categorized as a transconductance amplifier model. So the gain here, this is the gain, is a transconductance GM. Okay. Okay. And then in parallel with the dependent current source, we have small R node. Small R node is called output resistance. Okay, ideally, this small R node is very large or infinity. The value is infinity, and then we can remove the small R node because this small R node can be replaced by the open circuit. Okay, this is how we can calculate the transconductance R pi and R node. Okay, transconductance is given by this equation IC over VT. The VT is temperature equivalent voltage. So at VT will become 26 millivolt. This is at room temperature or 300 Kelvin. So in our course, we will consider the operation at room temperature. So the VT will be fixed at 26 millivolt. Okay. In order for us to calculate the GM, so you need to know the collector current. So the collector current here is the current at the Q point. So this means that whenever you want to do the AC analysis, you need to make sure that you have information on the Q point or DC analysis. Okay. In terms of as for R pi, R pi is defined by this equation. So R pi is equal to beta over Gm. So beta here is a DC gain. So this is a DC gain. Okay. For the output resistance is defined by VA over IC. So what is VA? VA is early voltage. So this is the voltage value depend on the device characteristic, and the value is very large. Usually VA is quite large, and then so that the R naught also become very large. So that's why in most cases we will assume R naught as equal to infinity. So and then we will not consider the R naught. Okay, this slide show the difference between NPN transistor and PNP transistor. Okay, the difference is the V pi polarity and current source direction. So apart of that, almost the same. So why this is the same? This is become like this because if you compare the symbol, the current direction between NPN and PNP. Okay, so if you this is NPN and this is PNP. So for NPN, the emitter current is exiting, so towards downward, and then the collector current, base current is entering. So this is IC and this is IB. So here the base current will towards the emitter, so this is IB. Collector current also towards the emitter, IC. Emitter will exit, so this is IE. So that's why the GM, the current direction for the current source is facing towards downward. For the V pi, because of the IB is flow downward, so V pi will become, the positive of V pi will become at up at this upper point, and this one is negative here. So this will consistent with the direction of the base current. Okay, but as for PNP, the emitter current is entering the transistor, and while the collector and base current is exiting the transistor. So we can have here, this is emitter current entering. So we have here collector current exiting. So this is consistent, as well as the base current also exiting. So the current in general should flow from the high potential to the low potential. So that's why the V pi, the polarity of V pi become like this. Okay, so when we use the amplifier BJT in amplifier circuit, we can have three main circuit configurations. So the first one is common emitter, and we can have common collector, we can have common base. So how we can identify the common emitter? How we can identify a common emitter is we see the terminal of the BJT. Let's say if the base and collector are connected to the output, input of the amplifier. So means that there will be one terminal that is unused. There will be one unused terminal, which is a emitter. So emitter will not be used neither as the output or nor the input. So emitter is the common terminal. So this is we call it common emitter. Okay. For example, if common base means that emitter and collector are used as the input and output port. For common collector means that base and the emitter used as the input and output port.